So last time we learned the formulas, the calculus for this polar curves. Curve will be something like this. Have a starting angle, ending angle. So for this curve, we give a formula for the area. The area, we have the area element. Sector area element. So in certain sense, if we use a differential element, differential. Okay. The first one we call it a difference. Second one we call it differential. Okay. So difference means different things in different contexts. In our case, the difference means if this changes, how the area changes. Then the total area. The total area.
Or with the thing next to it.
In this?
No, like
This?
yeah.
So if this if we have a parameter t, x, t, y, t, we have a, t, b. So the range of the parameter. So here, you mean this one?
Yeah, beta.
So this is alpha. In the Greek letters, how do you write alpha?
Yeah.
So this is the beta. How do you write beta? Okay, you don't. Okay. So I want to distinguish the two parameters. If we have t, we use a from a to b. If we use this angle parameter, the range will be alpha to beta, distinct to separate the two cases. So one's AB, the other alpha beta, make it comparable. Okay. Because sometimes we will integrate T for A to B, then theta from alpha to beta, want to separate them. So alpha is the starting angle and the beta is the ending angle. The polar curve changed from angle alpha to angle beta. Then this curve is bounded a domain. The area of this domain will be this. We integrate from alpha to beta 1/2 f squared. Now let me add a second curve. This. I assume this is r equals g theta. Again, alpha, theta, beta. Now I want to find the domain between them. Okay, could you give me a formula for the area of this part? The total area F is this. Who wants to try? Okay, Zichen wants to try, yes. Sophia, what would you do?
Subtract
Uh-huh, okay.
it
So,
and
yes,
um
so this will be the area bounded by F, and this will be the area bounded by G. The difference is what's in between. Okay, so the difference is similar to what we had for the regular case. Similar to what we have before, if we have a function, another function, the area in between will be the difference of the two integrals. A second formula is the arc length. Okay, the arc length of a polar curve, the square root, the square derivative square. Okay, so how do we get this formula? After the end of last class, I've added some details. Okay, so initial, okay, let me, initially it will be the square root of the summation of the square of derivatives. So that's from the Pythagorean theorem. In our case, for a polar curve, x is f cosine theta, y is f sine theta. The derivative of x, apply product rule. Derivative of y, apply product rule. The first square we distribute square, square, crossing, square, square, crossing terms. Then we observe this for this common factor, cosine square plus sine square equals 1. This one, they cancel with each other. Derivative function. Cosine, cosine, sine, sine. They cancel each other. Function square, sine square, cosine square, we add 1. So this gives us the derivative square, this gives us function square, they cancel each other. So we have the formula for the arc length of polar curve. That's the previous lecture. Okay, let's have a simple example. The simplest one, r equals 2. Okay, so this will be a circle of radius 2. Okay, Zichen, what's the arc length of a circle of radius 2? Formula. A circle of radius 2. Okay, so now that's not the formula yet. We have a circle of radius 2. What's the perimeter? Okay, 4 pi. Now we are going to check if our formula recovers this value. Okay, let's check. Check our formula. 0 to pi square root f square. F, so it's 2 square. Derivative is 0. Then we get okay, so what we expected. Okay, a second one. Second example, R is 2 cosine theta. Okay, now let's recall what's the geometric shape of this curve. Sakina, you know, it's a circle of radius. Okay, so let's see what's the equation. If we multiply both sides by r, we get r squared. So x squared plus y squared to x squared. Then I add 1 because I want a complete square. Then I get okay, what's the radius, Sakina? 1 or 2?
Oh, the base.
Is 1. Okay, what's the perimeter? Huh. Okay, let's put our formula into work. See if we recover 2 pi. And give a minute to work on this one. Let's apply our formula. Sakina and no, Sophia and Elisa also do the work. L equals to f theta square derivative theta square d theta. Do you recover 2 pi? Okay, Sophia, what's the limit? What's the lower and upper limit?
Um, I'm not sure.
Okay, so when we draw this, we go from 0 to 2 pi. If we go from 0 to 2 pi, we go around the circle twice. If we want to go around the circle exactly once, go from 0 to pi. So limit will be from 0 to pi. In this way, we go around the circle once. And who finished? Okay, which step?
Right, and then
What's F?
2
2 cosine theta. What's the derivative? 2 cosine theta. If you take a derivative, you get 2. What's that cosine? Uh-huh. Okay, so let's check. F theta g theta. If you take a derivative, what's the formula? Mm-hmm. The train you finished? From where? From here? Okay, so let's check from 0 to pi. Oh, my 0 is always, let me check where my 0. Okay, the train what's the first square? 4 cosine square. Second square, 4 sine square. Okay, 4 cosine square plus 4 sine square, what do you have? Do you have 4 and y? Okay, yes. Okay, again, we get what we expected. The arc length formula for polar curves. It's the square root of the summation of the squares of the function and its derivative. And this comes from the Pythagorean theorem from here. Okay, so this is about the polar curves. Now we start a new chapter about the sequence series and the power series. Okay. Have you learned this before? Sequence series? A little bit, okay, okay, that's good enough. And you? A little bit. Okay, okay, okay. So we have 2 lectures, okay, we will cover something. Okay, so the first part, sequence. Sequence, we normally use this where we start, if we start at 1, n equals 1, go to infinity. Or we can list all the entries, A1, A2, A3. Sometimes if the starting and ending point is known, we will go with sequences. Okay, Zichen, give me a simple sequence. A list of numbers. What the number would it be? All numbers. All the numbers. Okay, so the first sequence, all the numbers. 1, 3, 5, 7. So Kina, give me another sequence. 2, 4, 6, 8. Sophia, third sequence.
7, 10, 13, 16.
7, 10, 13, 16. Elisa, give me another one.
3, 4, 5, 6.
3, 4, 5, 6. Okay, okay. So you all have some pattern over there. Let me give you some 1, -1, 1, -1. There's also a sequence. Or if you go with 1, 1 square, 2 square, 3 square, 4 square. All the squares. Oh, I can go even crazier. 1, 2 to the square, 3 to the cube, 4 to the fourth power, 5 to the 5th. I can go the reciprocal. 1, so this descriptive. Another construction of a sequence, and I think I'm sure all of you have seen it before, Fibonacci. Okay, Sophia, have you heard of this before, Fibonacci?
Yeah,
So how is it defined?
it's like one. It's like one, and it you add like the previous two, so it's 2, and then 3, and then 5.
Okay,
Yeah.
each time we add the previous two, we're given the first two and the remaining one are defined recursively. So F1 Okay, so this recursive definition. Definitions are different. Okay, so this two-step recursive definition. The one step, let's see, we go another one. A1 to AN. Okay, so this is another sequence. We know A1 is 1, and AN will be the product of 2 with the previous one, twice of the previous one. Okay, the Zhen was A2. So can A4, 3. How do you get that? 2 times 2, nice. 2 times, not 2. Okay, another example. A1 is 0. AN will be 2A1 1 plus. Sophia, what's A2?
1.
Elisa, A3.
3,
Zichen, A4. Seven. Okay, Sakina, A5. 15. Okay, so now given the formula, we can compute the sequence one by one. Sometime when we are given a formula, we will try to recover we give a sequence, we try to recover the formula. Okay. For some sequence, we can study the limit. For example, the limit We all know this is 0. And let's see, what's this limit? This is 0. What about this?
There's no limit.
Okay, we have one answer
Wait,
here.
actually, never mind. It
Uh-huh.
sign 0.
Okay, and what's your argument? Why? Because when n increases, this becomes smaller and smaller to approach 0.
Yeah.
Sine is a continuous function. So this goes to sine 0.
So just 0.
Okay, so this is a very important property of sequences. Suppose suppose we have a sequence that the limit is L, and we are given a continuous function. In this case, the limit of this new sequence is given by the value of f at the limit. In certain sense, we say the limit can commute with continuous functions. Limit commute. That means the limit whether we take the values, then limit, or we take the limit, then the value. It doesn't matter if the function is continuous. Another one. Let R be a number. Oh, that's right. R is a number. A real number, what's the limit? R to the power. Think about this limit. Is there a uniform answer to this question? Or we have to divide it into cases? Okay, what's the first case, Chen? When, okay, that's the easy one. Okay, so R is 0, what's the limit? Okay, R is 0. So can I give you another case? R is 1, this is 1, okay. Sophia, a different case.
R is between 0 and 1.
0 and 1. What's the limit?
0.
Okay, and why is that?
Because it just if
So
it's less than
smaller,
1,
smaller.
it's getting smaller and smaller and smaller.
Okay, okay. And Elisa, another case.
-1.
R is -1. What's the limit?
Negative.
Okay, so if okay, okay, I said -1, but I wrote 1. Okay, mistake. If it's -1, then the power. So when n is 1, -1, n is 2, 1, -1, 1, -1, 1. So to oscillate between the two values, in this case, the limit doesn't exist. And in general, if the absolute value of R is bigger than 1, summary, if it's bigger than 1, then it doesn't exist. If it's less than 1, it's 0. If it's 1, so we call this its geometric sequence. Let me check with you about this. Okay, so A1 is 2. AN will be 2 plus square root of AN plus 1. Okay, Zichen, what's A2? Sakina, A3. Apply this formula. Do not simplify, just do the result. Do not simplify. And Sophia, A4.
2 plus square root of 2 plus square root of 2 plus square root of 2.
Elisa, A5.
2 plus square root of 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 2.
All right, now we have 5 of them. Now let's guess in this sequence. So what's the pattern? The bigger or smaller or constant? Bigger. So in this each time, this goes bigger. This goes bigger. This goes bigger. Okay. Now we want to see, is there a limit? It gets bigger and bigger, but is there a limit? If there is, how do we find the limit? Okay. Goes bigger and bigger. Could this reach 10? Could it go bigger than 5? How do we answer this question? Okay, one observation. We'll start with, okay, I need a different color. I claim this is less than 4. That's clear? Now, is this less than 4? Why? Because over there is less than 4. The square root of this is less than 2. So square root less than 2. What about next one? Is this less than 4? And why? So this whole thing is less than in the previous step. So this also in the previous step. Now the observation is, even though it's increasing, but it's bounded from above by 4. So here we use, okay, the method. What's the method to prove this argument for all n? We verified a few. How do we verify this for all n? There's a term. Okay. Now you know. So as long as you that term cross your mind, you know where to go. Mathematical induction to prove this for all n. Okay, so now we have an increasing but bounded sequence. So we know the limit exists. We don't know what it is, but we know the limit exists. Use x. It's the first step. Limit exists. Next, we will try to find this limit. To find this limit, let's use the formula. I'm going to copy x. What we don't know is defined as the limit. Nothing changes. Next, I'm going to use the formula. An is defined as 2 plus this. So I'm going to use this formula, 2 plus. Now, how do we take a limit? Sophia, what would you do? This is a continuous function of the sequence. The limit of the continuous function will be the continuous function of the limit. We apply the previous theorem. This will be 2 times limit. Okay, let's compare this one with this one. They correspond to the same sequence, just with a shift. In particular, they should be the same. Do you agree? Okay, because so this one is an, a1, a2, a3, a4. An minus 1, so we shift it by 1. Still has the same limit. Okay, this is a very important step to convince yourself this works. Okay, so we don't know what this limit is, but we have an equation for it. Now we have this equation, how to find x. How to find this x? Just think. How do you do this one? Elisa, how do we find x from this equation?
Square both sides.
Okay, one approach, we square both sides. We want to get rid of the square root. So I will subtract 2 to isolate the square root. Then I square. This is x squared minus 4x. So we can factorize this. Okay, so we have 2 choices. Which one do we pick? Why? Why? Okay. So we put this into the formula, it doesn't work. Okay, so we get rid of it. And this one works. So with this sequence, increasing become more and more and more complicated. But it has a limit, which is a very nice number 4. Okay, any question about this one? Okay, if I change this to 3, do you know how this goes? Each time start with 3, 3, 3. Again, you get the sequence, you should be able to find the limit. Another construction. Okay, this time do not simplify, just give me the expression. A1 is 1, AN is 1 over 1 plus. Let's think about this. Okay, this works. Okay, let's again the chain. What's A2? Do not simplify. Sakina A3. Sophia A4.
1 over 1 plus 1 plus the over 1 plus 1 over 1. Wait, 1 plus 1.
And Elisa A5.
1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1.
Okay, again, it's getting more and more complicated. Okay, now let's see. A1 and A2, which one is bigger? Zichen? This one is bigger. Let's compare A2, A3, which one is bigger? Sakina. Compare the denominator, which one is bigger? The 2 is bigger, then the 2, which one is bigger? This denominator is bigger, so this number will be smaller. Okay. Now, Sophia, A3, A4, which one is bigger?
Is
Let's compare the denominator, which one is bigger? Denominator compare this two. This time, so this is bigger, then this will be smaller. This will be bigger. So this is different from what we had before. So it goes back and forth, but it becomes closer and closer. So the picture will be like this. Let me draw a picture for this. A1, A2, A3, A4, A5, A6. It jumps back and forth, but it will converge to a middle point. Okay, so let's denote this x as the limit. How do we find this limit? It should be something between this is 1, this is 1/2. It will be something between 1 and 1/2. So what's this number? If we go to the previous one, how did we find this limit? We use definition to get an equation about x. Now what would we do? Get an equation. Okay, very nice. We will use this formula to get an equation. Let's try to get some space so we can have everything in one piece. I'm going to move this one a little bit to the left. This one a little bit to the upper. The space to do the calculation. Using the formula limit. Okay, so it's b1 plus an minus 1. Again, the continuous function, so it is will be 1 over 1 plus the limit. Okay, so now what's this limit? This one is x. The difference is very similar. It's 1 plus, just 1 plus x. Okay. Okay, now we have the equation x equals 1 plus x. How do we find x? Okay, give you a few minutes. Think about it. How do you find x? Multiply x. This equals 1. How do you solve this quadratic equation? I would go with the completing square. So if I want to complete square, what do I add?
One-fourth.
Okay, Sophia said, okay, 1/4. So then this is x plus 1/2 square. Take a square root. Then we subtract this. We have two choices. Okay, which one do we pick? Oh, and what's the reason for this? Nice. So all of our numbers are positive. In more precise, it's between 1/2 and 1. This one is negative, it's not in our range. So that's our choice. We remove this one, pick this one, and we simplify it a little bit. So this is approximately. Have you seen this number before? Sophia and Elisa?
No.
So this number is called the golden ratio.
Oh.
Okay, heard of it. Okay. Golden ratio. Okay. Okay, so let's have 5 minutes break and we'll be back at 55. Okay, so this construction is called the continued fraction. This is called give a sequence of numbers, we can construct the continued fraction. Another example is if we go with 1, 2, 3, 4. So this is a continued fraction. At each position, we put a number over there. But that this goes on and on. Again, we have the same thing. It's bounce back and forth. Eventually, it will converge a number. So how to find that number? Is it rational or irrational or even some other properties? So it's not easy. This is one example of the continued fraction. More general case. Has many applications. Okay, so just give you an introduction of this. Next, we'll move to theories. We will recall the summation notation. We add this from M until the last one. And we often consider the infinite series. We add A1, A2, and we continue infinite series. Sometimes when we're adding them, after we're adding them, we get a number. But sometimes we don't get a number that is divergent. Mm-hmm. Or okay, no injuries. Okay. 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 So the previous example, the exercise is called continued fraction. So you can say this is a fraction, another fraction. We continued this way. So the names continued fraction. More general construction. It don't have to be one, and the number can change. So 1, 2, 3, 4, and give any sequence of number, you can apply the construction. You get a continued fraction. But the difficult part is how to find the limit. For this one, it's extremely difficult to find what the limit is. We know the limit exists, but we couldn't find it. We don't have a formula for it. And like the previous one, we find, oh, this is the golden ratio. Then we move on to series. So series, we add a sequence of numbers. The study of a series is closely related to the study of sequence because we can introduce the sequence of partial sums. We use Sn. So from a series, we construct a sequence of partial sums. S1, that's the first term. S2. And we have the recursive formula. Sn will be Sn. The previous one, add a new entry. Okay, Zichen and Sakina, have you seen this before? The partial sum. Okay, okay, nice. And Sophia, what about you? Partial sum. Unmute yourself, Sophia. Have you learned this partial sum before?
I think I might have seen that.
Okay, okay, okay. So let's have some exercise, some practice about this. If our sequence is 1 over to the n, we want to study the series. We start with the partial sum. How to find this number? Okay. Okay, okay. You also saw the formula, right? So there is a formula, okay. So the formula is about sigma. So r to the nth power. The partial sum in this case will be r square r to the n. To find the formula for this, we multiply both sides by r. R square. Then we find the difference. So difference 1 minus r. All the intermediate terms cancel with each other. Only the first and the last term survive. So with the partial sum, we have a formula for the partial sum. When r is not 1, then we apply it to the previous case when r is 1/2. One half, 1/2, 1 minus 1/2. Okay, so it's 1/2, 1/2, so it will be 1 minus. Okay, now Zichen, what's the limit of this sequence? When n go to infinity. 1 because this goes to 0. Limit. In this case, we see the series is convergent. And it converges to 1. Okay. So even though we have this equality, we say it converges to 1, not it equal to 1. In some sense, it's the same, but we just make the distinction. It converges to 1. Okay, now the remaining case, if R is not 1, we have this formula. What happens if R equals 1? What's the partial sum? This case, it's easier. R is 1, all of these terms, 1, 1, 1, 1, we have n ones. The result is just n. Okay, nothing strange, just okay. Then the general case, sigma. Okay. As we have seen before, this will be the limit of the partial sum, which is R minus R. We assume it's not 1. This one, if the absolute value is less than 1, this will be R 1 minus 1. If the absolute value is bigger than 1, the divergence doesn't exist. The special case when R equals 1 to go to infinity also doesn't, sometimes we see infinity, sometimes we see doesn't exist. -1 doesn't exist. So this case, we may say doesn't exist if the absolute value bigger than or equal to 1. Geometric series. So if the limit of the partial sum exists, then we say it's convergent. If the limit doesn't exist, it's divergent. Okay. So there's a very useful test for divergence. If the limit of the entry does not exist or not 0, series is divergent. One example will be this series. Okay, Zichen, what's the first term of this series? -1. Sakina, second term. 1. Sophia, third term.
-1.
Elisa, fourth term.
1.
1. For this one, if we check the partial sum S1, S2 will be 0. S3 back to -1. S4, 0. So we can see the partial sum, this sequence oscillate between -1 and 0, -1 and 0. So the limit doesn't exist. This implies the series is divergent. Okay. So, but in some case, this test is not good enough. The entries may have limit 0. Is the series divergent or not? We are not sure. This series okay. Have you seen it before? This series. There's a name for it. What's name? Summation of all the reciprocal integers. We call this the harmonic series. Now, if we find the limit of this, we go to 0. But is this convergent or divergent? How do we determine that? So for this one, we have a new method of the integral test. To check whether the series is convergent or divergent. The following setting, where f positive and decreasing. Okay, now we have two objects, the series, the sequence, and the function. We have two objects, n equals 1 to infinity, an, the integral. So on the left is the series, on the right is the integral. Under this condition, that the function is positive and decreasing, these two, if one is convergent, the other is also convergent. If one is divergent, the other one must be divergent. We use this notation. It means if one is convergent, so is the other. So this is why we call it the integral test. In order to determine if it's convergent or not, we compute the integral of the corresponding function. Okay, let's use this method to check the harmonic series, whether it's convergent or divergent. Okay, so for this one, we should guess a function. A n is 1 over n. What will be our function? So for some function that is positive and decreasing whose value at n is 1 over n. Sophia and Elisa,
Um,
so this, Sakina, you have an idea? Or? Yes, okay. Anything. So for this one, I'm going to pick the function 1 over x. Now if we check if x equals n, we get 1 over n. Okay, to determine whether this is convergent or divergent, we apply this test. So we need to compute the integral. Is this integral convergent or divergent? Okay, what's this integral? Okay, so this is an improper integral. It will be the limit b equal to infinity. 1 to b lnx 1 to b. This will be limit b equal to infinity ln b. So this one is called infinity, which is divergent to infinity. Since the integral is infinity, we claim this series is divergent. This is our first example, 1 over n. We have a similar one. If we replace it by 1 over n squared, convergent or divergent, how do we check? Okay, think about this. What function would you pick?
one over x squared.
So we have one response, we pick x squared. If we use x squared, well, x equals n, 1 over n squared. This is, okay, now we need to check if the integral is convergent or not. How do we find this integral?
Limit as
Limit, okay, limit from 1 to b, 1 over x squared dx. 子晨, what's this integral? From so 1 over x squared. One over x dx. This is, oh, sorry, I forgot square. Okay, check. If you see lnx, could you recover squared? If you take a derivative, do you recover this? Okay, so this is a very special one. So this integral with ln, it's very special. That's the only case we have ln. So here it will be a power. One over x. Okay, this now we can check if we take a derivative, we get this. So this lnx is a very special. It's the only case when the integral of a power is not a power. As long as it's not 1 over x, the integral will still be a power. We just need to figure out the power and the coefficient. Okay, so this will be negative 1 over x, 1 to be negative. I forgot, let me copy the limit. Okay, the integral converges, so by our theorem, this implies the series is convergent. Okay. But there's a very important point over there. Both are convergent, but they converge to different values. It does not mean they are the same. Okay. So even they don't have. Okay, that's not easy. It's a very difficult question. In some case, we can check. We develop some tests to determine is it convergent or not. For example, this integral test give us a method to check it's convergent or not. Divergent.
Accepted.
Then so it's
Wait, so if it's infinity, it's divergent. What about convergent?
so if this we get a fixed number like this, then it's convergent. Very good question. In general, it's very difficult to determine is it convergent or not. So we develop one test for this case, another test for that case, more and more tests will come. So an important fact of this, we don't have, okay, let me emphasize, we don't have. Okay, so this is not true. In particular, we know the integral of this 1 over x squared is 1, but the summation is something very strange. Zichen. You saw it before? No? Okay. Pi squared over 6. So the addition of the reciprocal of the squares, they are all natural numbers or rational numbers, but the result will be an irrational number. Okay. Sophia, any questions?
No.
Okay, so the point is, these two, even when they are both convergent, they converge to different things. The integral converges to 1, series converges to pi squared over 6. Okay, let's try the last one. Summation. This time we start from 4. Convergence or divergence? How do we determine? Check. Limit of the integral. So okay. So what's the function? Okay, now we integrate 4 to infinity. Dx limit. Okay, now we need an antiderivative of this. How do we find an antiderivative? Something. How to find this antiderivative? So if we ignore this logarithm, what do we have? We have the antiderivative will be logarithm x. Now we have an additional one. So we can use U substitution. This U then that will be 1 over the du 1 over x dx. This becomes u du. Okay, right? Yes. Okay, no, let me okay, so what's the integral of 1 over u? And u, because with here they are all positive, so we drop the absolute value. Nice. Double ln x. Okay, so we found that this function will be the limit to infinity ln b ln 4. Okay, what's this limit? When b go to infinity, what can we say about this logarithm? Sophia?
It goes to infinity.
If this goes to infinity, what about the double logarithm?
It also goes to infinity.
Okay. So this go to infinity. Okay, now the integral diverges. What can we say about the series? Also diverges by the integral test. Nice. This implies so here we start at 4 because if we start at 1, logarithm of 1 is 0. 0 on the denominator is not allowed. This is the only reason we start at 4. You can start at 2, 3, doesn't matter, but not at 1. Okay, so we stop here today. Okay, see you next week. And we'll be homework and office hour tomorrow. Okay, don't forget your homework.
Thank you.
Okay.